So today we are starting graphing rational functions. This is the beginning of our rational functions unit, which is only 4 sections. So we probably like that to get your spring semester off to a good start. Okay, so we're going to start with graphing. And graphing looks like it could be complicated, but really the rational expressions follow a lot of the same rules that all of our other functions do. So this is our standard form of a rational function. And what makes it rational is that now we're dealing with fractions. But the shifts are kind of the same as they are in other functions. So that h is going to give us our horizontal shift. Remember, in our other functions, it was always the opposite of that, the opposite of what you see. And k is going to give us our vertical shift. And that a is a little bit different here. In other functions, it tells us how much our function stretches or compresses, but really in rational functions, it tells us how far away from the middle that we are. So kind of a stretch, but a little bit different. Okay, so here's the parent function for a rational expression. And so what actually happens is if we plug in 0 for x, well, 1 divided by 0 is undefined. We can't have that. So what really happens is that at 0, just like if you have a linear function that has a slope that's undefined, it's actually a vertical line. So with a rational function, the parent function, you have a vertical asymptote right on the y-axis. Okay. You also have a horizontal asymptote right on the y-axis. So really the middle point that you're looking at is still 0, 0, because everything kind of rotates around that point. That's important when we start shifting them, and you'll see that in a second. So for this, our horizontal asymptote is at y equals 0, and our vertical asymptote is at x equals 0. Okay? So everything's going to kind of shift off of this parent function. So just think about when we've had functions before with the horizontal shift going on here. We set that bottom, that denominator equal to 0 and solve, which gets us x equals 3. So now we know that our vertical asymptote is going to be at x equals 3. We also know that this number out here, which is our k value, gives us our vertical shift. So that means it's going to shift. So this is shifting us to the right 3. This is shifting us up 5. So our horizontal asymptote is going to be at y equals 5. So let's go ahead. This point right here was 0, 0. I'm going to go ahead and put my middle point at 3, 5. I'm going to move that point over 3 and up 5. That's now the middle of my graph. And I'm going to go ahead and put in my horizontal asymptotes right now and my vertical asymptote. Remember that asymptote is just an imaginary line that your graph cannot touch. If you looked at these microscopically, they would come really, really close to the asymptote, but never actually touch it. Okay? And then we can just sketch in our graph on either side. This is going to come really close to both asymptotes, but never touch. Okay? So let's do the same thing here. This is going to give us a horizontal shift to the left of 5 and down 2. Which means that our horizontal asymptote is now at y equals -2, and our vertical asymptote is at x equals -5. So our new middle point will be -5, -2. Here we had 5, 3. Back here we had 0, 0. So I hope you see the relationship between the asymptotes and that kind of middle point, which is not actually a point on your graph. It's just kind of a midway point for us to get our graph started. So we're going to put that point at -5, -2. And we can go ahead and put our asymptotes in right there. Nothing else about the graph has changed at this point, except that now, previously we had 1 in the numerator, now we have 3. What that really does, the shape is still going to be the same, but it's going to kind of bend out a little bit farther than a graph that has 1 as the numerator. I'm not really overly concerned about that at this point. I want the general shape and shift of the functions. So Okay, so now let's go down to y equals negative 1 over x plus 4. And I want you to think about in previous functions, when we had a negative here, what did that do to our graph? And that negative always tells us that we have a reflection going on. So let's get the basics of our shift going on here first. So in the denominator I have x plus 4, which means I'm going to have to shift to the left of 4. So my vertical asymptote is at x equals negative 4. I don't have anything being added or subtracted out here, so my horizontal shift is nothing. So my horizontal asymptote is going to be at y equals 0. So my new middle point is going to be at negative 4, 0. So let's go ahead and put that point in. Go ahead and put our asymptotes in. But now what that's going to do is that's going to reflect. So instead of it coming here and here, we're actually going to reflect both of those across that x-axis. So it'll look something like that. Okay. The next two we're going to do without, we're just going to sketch our own graph, and that's completely fine. So our horizontal asymptote, this is going to shift it to the right 7 and down 12. So my horizontal asymptote is at y equals negative 12. My vertical asymptote is at x equals 7. So there's my graph. My new point will be at 7, negative 12, somewhere down here. And then I can go ahead and sketch my asymptotes in. I don't have any reflection going on. There's no negative up here. So it's going to look just the same. It's going to sketch something like that. Okay. And finally, negative 5 over x plus 9. So let's think about what we've got going on here. I know I've got a reflection. My denominator is not shifting at all, so my vertical asymptote is just going to be at x equals 0. But it is shifting up 9. So my horizontal asymptote is going to be at y equals 9. So my new middle point will be at 0, 9. And I know that that's going to reflect eventually. So let's get our point in there. It should be 0, 9-ish. There. Put in our asymptotes. And normally this graph would, because of that 5, it would kind of push out a little bit farther out here, but that negative is going to reflect it. So it's going to actually look more like this. So what that 5 does is it really pushes this kind of point where it turns farther away from your intersection of the asymptotes. Like that. And I'm not going to be really specific about that. We can plug in numbers and make that really accurate and really specific. At this point, I really want you to just understand how to sketch the functions and learn how they move and their behavior more than anything. Okay, so sometimes you're going to see graphs of rational functions and they are going to look crazy and you're going to think, what is going on here? But even just by looking at them, we can find all these different bits of information. So let's look at horizontal asymptotes. Does it look to you like there's probably a point where these lines approach but don't touch? And to me, that looks like it's at y equals negative 2. So I'm going to go ahead and put that line in there. And that's the only horizontal asymptote I see. Vertical asymptotes actually looks like we've got more than one. So I see one at x equals 2, and I see another at x equals negative 2. So we've got x equals 2 and x equals negative 2. Yes, it is possible to have more than one of either type of asymptote. It just depends on the function. The more complicated they are, the more asymptotes they can have. Okay, so x-intercept. So think about what an x-intercept means. That always means where our function is intersecting the x-axis, and those always have a y value of 0. So let's see where we have any of those. So there's one right there, there's another one here, and they look like they're right over 2 and negative 2, right before 3. So let's say they're 2.5 roughly and negative 2.5. Okay, just an estimate. Then our y-intercept, of course, is anywhere where our graph intersects the y-axis, and it always has a y value of, or excuse me, an x value of 0. So that looks like it's going to be at this point right here, which would be at 0, negative 3. Okay, asymptotes, intercepts are very helpful in graphing rational functions. When we go to the next page, you'll see that we're starting with the equations and working back to the functions. So it just helps get a kind of a viewpoint of what we're doing first. Okay, and let's look at this one. So we've got all kinds of things going on with this. So let's look at horizontal asymptotes. So we do have one. Now the horizontal asymptote may not apply to this middle graph, but it definitely applies to the outline graph. So that looks to me like that horizontal asymptote is at y equals 1. Vertical asymptotes looks like I've got one here at 3 and another at negative 2. So I've got x equals 3 and x equals negative 2. Okay, let's look for any x-intercepts. So I've got one here and I've got another here. So it looks like I've got one at negative 4, 0, and that looks like at about, I don't know, 2.5, 0 maybe. Again, we can just estimate right now, it's fine. And then the only y-intercept I see is right here, which is about what, 1 and 1.5, so 0, 1.5. Okay. So I think my screen blanked out for a moment. So my horizontal asymptote, the only one I have is right here at y equals 1. Vertical asymptotes, I've got at 3 and negative 2. And then my x-intercepts I see here at 2.5 roughly and at negative 4. My only y-intercept I have at 0 and about 1.5 or so. Okay. Okay, so now let's get into algebraically how we would find those asymptotes. If you're going from a graph, it's pretty easy to see those, but algebraically we need to be able to find those asymptotes also because that will help our graphing be very, very easy. Definitely easier to do if you have things in factored form. We'll talk about that a little bit later. But your vertical asymptote is, think about what that is. That is where the graph is undefined. Which means where the denominator equals 0. Because we know we cannot divide by 0. That is undefined. So that creates that vertical asymptote. Horizontal asymptotes are not quite as straightforward as that, but they're actually pretty easy. There's some rules to that. So if the power on the bottom is bigger than your, and when I say power, we're talking about the degrees. So if we look at this, this is a first degree, second degree. If the power on the bottom is bigger, then your horizontal asymptote is always at y equals 0. Okay. If the degree on top is bigger, the leading degree is bigger, then there is no horizontal asymptote. If the powers are the same, it is the ratio of the leading coefficients of the numerator to the denominator. Okay, so now that you've got those rules there, and we'll explain this in just a second. So, the degree in our first example, power on the bottom is bigger, which means that our horizontal asymptote is always going to be at y equals 0. Okay, so let's figure out the vertical asymptote. We need to figure out where that denominator equals 0. So if we have x squared minus 4x minus 32, what we really need to do with that is factor that equation. So, because then we can set each of our factors equal to 0 and solve, and then we've got the two spots where they will equal 0. So, the two numbers that I can multiply together to get negative 32 that have a sum of negative 4 would be x minus 8 and x plus 4. Each of those being set equal to 0. I would get x equals 8 and x equals negative 4. Those are going to be my vertical asymptotes. Because the degree on the bottom is bigger, I have a horizontal asymptote of y equals 0. Okay, the power on top is bigger. There's not going to be any horizontal asymptote. And really the reason for that is that if I divided x squared by x, you take all the other numbers out of it. X squared divided by x would give me x, which is in itself its own function. That would just be a linear function. So there's no place where that function doesn't work. So the horizontal asymptote is always going to be at, there's not going to be a horizontal asymptote. In order to find the vertical asymptote, again, I just need to set my denominator equal to 0 and solve, because I cannot divide by 0. That gives me an undefined answer, which means that that's where my vertical asymptote is going to occur. So my vertical asymptote is going to be at 9/4. Okay, horizontal asymptote here we have, let's do that one first. So the powers are the same here. My degree of both equations is x squared, so my degree is 2. So what I really need to do is take the ratio of this number together. So my horizontal asymptote is going to be at 1/3. Just that easy. Okay, again, we need to factor the bottom to find our vertical asymptote. So 3x can go into 3x squared and 21x. So I'm going to go ahead and factor that out and then set each of them equal to 0. So if 3x equals 0, then one of my vertical asymptotes has to be at 0. And x plus 7 equals 0, then my other vertical asymptote is going to be at negative 7. Okay, let's find intercepts. So remember, for x-intercepts, your y value is always 0. For y-intercepts, your x value is always 0. That's something we just know. Y-intercepts always intersect the y-axis, x-intercepts always intercept the x-axis, and those are always going to be true for those points. Okay, so let's think about our x-intercepts. That means that this function is where our y value or our output is 0. So it's where this equals 0. So if we can get our numerator to be 0, 0 divided by anything is 0. So really all I'm concerned about is that top, where that equals, or the numerator equals 0. So in this case, I'm going to get a point of negative 3 halves. If I have negative 3 halves here, 2 times negative 3 halves is negative 3 plus 3 would be 0. 0 divided by anything would give me 0. So my x-intercept for this equation would be at x equals negative 3 halves. My y-intercept is going to be where my x value equals 0. So y-intercepts are kind of easy because we can take our whole equation, and anywhere that there's an x, we're just going to plug in 0 and then solve. So we get 0 squared minus 4 times 0 minus 32. Well, all of this just equals 0. So my y-intercept is going to be at negative 3/32. Okay. Let's try another one. So remember, my x-intercept is going to be where my numerator equals 0. And my y-intercept is going to be where I plug in 0 for x and solve. So really pretty easy on both. So again, I have x squared plus 5x minus 36 in my numerator. Well, in its standard form, it doesn't really help me. Factored form would help me a lot more. So the numbers that multiply to negative 36 to add up to negative 5 would be x minus 9 and x plus 4, setting those equal to 0. So one of my x-intercepts, and yes, you can have more than one of my x-intercepts would be at 9, the other one would be at negative 4. For my y-intercept, I'm going to go ahead and plug in 0 everywhere that I see an x. So in this case, I get x squared plus 5 times 0 minus 36, and then 3 times 0 squared plus 21 times 0. So now the problem I've got is I've got negative 36 over 0, which is undefined, which means that that cannot happen. So there is no y-intercept in this case. That's possible too. Okay, so now let's kind of put all of that together in this problem here. So definitely I think helps if you have everything in factored form. So I can see that that bottom function needs to get factored. And I know because that's a perfect square, and there's a negative in the middle with no middle term, that is a product of a sum and a difference. So that's x plus 3 and x minus 3. So my vertical asymptote is going to be wherever my denominator equals 0. Since this is already factored, I can just take the opposite of my factor. So that would be at x equals negative 3 and x equals 3. My horizontal asymptote, in this case, the degree of the top is smaller than the degree of the bottom. So my horizontal asymptote is at y equals 0. My x-intercept needs to be wherever y equals 0, which means it's where my numerator equals 0. So 3x minus 5 equals 0, 3x equals 5, so x equals 5/3. And then my y-intercept is going to be wherever x equals 0 when I plug in. So 3 times 0 minus 5, and 0 squared minus 9. So that gives me a y-intercept of 5/9. So let's kind of put all that together, shall we? So I've got vertical asymptotes at negative 3 and positive 3. I've got horizontal asymptote there. I've got an x-intercept at 5/3, which is just under 2. And I've got a y-intercept at 5/9, which is just about half, which is kind of there. So what happens in this graph actually is you've kind of got a couple things going on. You have your standard rational function graph out here on the outskirts. And then in the middle, you've kind of got this extra little, almost looks like a cubic function going on. Okay, so that's what that's going to look like. And sometimes you're going to ask me, well, how do I know if that's going to start at the bottom and work its way to infinity? That would be if you had negatives going on out in the front here. You'll see as we graph what the patterns are going to be. So that's graphing. We'll have more practice on it, and see you soon.